Hey class, today we are going to dig into the next part of chapter 6, which is all about radical expressions. Now, the first thing we want to do when we're talking about radical expressions is understand what we're talking about. A radical is a inverse of squaring or cubing or using any type of power that we are raising that base to. Finding the radical will help us undo that. Now, when we are talking about radicals, it's important to know what the different pieces of the radicals are. So when we talk about the radicand, that is going to be the term that is inside the radical. For example, here it is x. That radicand is what we are going to be simplifying today. Now, the other pieces of the radical are the sign itself, totally radical, dude, and the index, which for now is, going to stay 2 to represent the square root, but that could be any root and any degree possible. Now, what we're doing today is we are rewriting our square roots by finding pairs of perfect square factors that are hidden inside of the radicand, meaning hidden inside that radical sign. Before we can start hunting for those perfect square factors, we need to understand what perfect squares are. So let's review our perfect squares. Now, we're not going to go through all of them because the list goes on indefinitely, but the first 10 are often the most used. So that would be 2 times 2. Our first perfect square is 4. 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 6 times 6, 36. 7 times 7, 49. 8 times 8, 64. 9 times 9, 81. And 10 times 10, 100. So those are our first 10 perfect squares. We get them by multiplying the base by itself, and then the perfect square is the results that we get when we square those bases. So 4, 9, 16, 25, 36, 49, 64, 81, 100. Those are the factors that we are looking for within our radicals today. Because if there is a perfect square hidden within this radicand term, whatever term is inside the radical, that means we can factor that out by taking the square root and moving it outside of the radical sign. So let's see what that looks like. If we have a radical, for example, the square root of 63, and they ask us to write an equivalent expression for that radical, we are going to try and find the perfect squares that we can fit within that radical. There's a couple ways to do this. I personally like to find just all of my factors. So we're going to find all factors. And in fact, we want to look for prime factors. That's really going to help us find these perfect squares. So if we have the square root of 63, we can break that down. The first thing I think of is 9 times 7 and 3 times 3. So this would become the square root of 3 times 3 times 7. Now, when we break it down into those factors, those prime factors, we can more clearly see where we have a pair. In this case, our pair is a pair of 3s. Now, if we think back to the definition of what a squared number is, a number raised to the power of 2, that means we're multiplying a number by itself. Well, here we can specifically see exactly which number is being multiplied by itself. 3. We have a pair of 3s. So, if we take the square root of those 2 3s, it's the same as taking the square root of 9. And the square root of 9 is 3 times 3. So when we take the square root of these two numbers, of these two terms, because they're a pair, we move it outside the radical. So the square root of 9 is 3. And then 7, we can't factor that any further. There are no perfect squares hiding in there. There are no more pairs of numbers. So we just keep the 7 inside the radical. Now our simplified equivalent expression for the square root of 63 is 3 square root 7. So that's what we are going to be doing today. Let's do some more examples. So the square root of 44. If I break that down into my factors, let's start with 44. The first factor pair I can think of is 4 and 11. 11 is prime, but 4 we can break down to 2 times 2. So now we have 2 times 2 times 11. Well, when I do that, I see I have a perfect square pair. 2 times 2, that would equal 4. So because I found my pair, I can move that number outside of the radical. So it is 2, because the square root of 4 equals 2. That's the same as saying the square root of 2 times 2 equals 2. So when we take the square root, we move it outside. And then the numbers that aren't perfect squares, those are stuck inside the radical. Now, the reason we're doing this is because we want to work with simplified terms. And if we were to take the square root of 44, we would get a very ugly decimal. And if we were to try and use that decimal in an equation, we would have to simplify it, which would take away our accuracy. So in this case, we want to use a simplified way of writing our radicals so that we can work with them in equations and expressions. So that would be our final answer. Now let's look at this next example, the square root of 2 to the 7th times 5 squared. So for when we have exponents involved in the radical, there's a couple ways to look at this. We remember that we're looking for pairs. And the reason we say pairs is because they represent a perfect square. So our first option is to write out all of our factors. So 2 to the 7th power would be 2 7 times. 4, 5, 6, 7. And then 5 squared would be 2 5s. Now, once I've written that all out, I can hunt for those perfect square pairs. So that would be a pair of 2s, another pair of 2s, there's a third pair of 2s, and then we have a pair of 5s. So we have found all of our pairs, and now we want to move them outside of the radical. So the square root of 2 times 2 is 2. The square root of 2 times 2 is 2. The square root of 2 times 2 is 2. And the square root of 5 times 5 is 5. Then we look at what's left. The only thing left over is this 2 here. So that's going to be the only number left inside our radical. Now to finish this up, we've got to simplify it. So we're going to multiply. 2 times 2 is 4 times 2 is 8 times 5 is 40. Square root 2. And that is our final answer. Now, the other option, and this is the one I recommend once we're more comfortable with this skill, but the other option is to recognize that we're looking for perfect squares, right? So if I have 2 to the 7th, and 5 squared. Well, 2 to the 7th is 2 squared times 2 squared, because remember, if we have the same base, we're adding the exponents, times 2 squared, 2, 4, 6, and then one more is 2 to the 7th power, and then 5 squared. Now I can see still exactly how many pairs we have. 2 squared is 4, so we move it out. 2 squared is 4, move it out. Another perfect square pair, but with exponents, and a third one. So we would still end up with 40 square root 2. Okay, if you need to, rewatch that just to make sure it clicks and it makes sense. Hopefully I explained it pretty well, but there are indefinite replays here in this video, so watch it as many times as you need. In our next example, we have 3 square root 27. Now, the only difference here is that we have a number on the outside already. And that's fine. We're going to kind of ignore that until the end. So I'm going to rewrite my problem as 3 square root. And then for 27, I'm going to find my factor pairs. So 27, the first thing I think of is 3 times 9. And then 3 times 3. Now that means I have 1, 2, 3 threes. From here, I look for those factor pairs. We have 1 pair of 3s, so we can pull that out. But now we already have a number outside of that radical. So if we have 3 square root, and we pull out our perfect pair, we're going to multiply that outside term by 3, by the number we have found the square root of. So then, or by the square root of our perfect pair, I should say. And then 3 is still left over, so that goes inside the radical. Now we multiply and we get 9 square root 3. And that would be our final answer. All right, the next skill we are going to practice is now multiplying these radical expressions, so multiplying one by another. In this first example we have here, we have 3 square root 5x times 2 square root 15x cubed. Now you might be saying, wait, there's variables now? Yes, there's variables, but it's okay. So the first thing we want to do is just combine the similar terms. So for example, we're going to combine the two numbers that are outside the radicals. And by combine, we're going to look at our operation here, and it is multiplication. So we're going to move 3 times 2 outside of our radicals, and then 5 times x times 15 times x times x times x, because x cubed is 3 x's, just in case we forgot. So now I have this written out in a way that I can find factor pairs a little easier. However, 15, we want to rewrite with prime factors. So that would be 5 times 3. So I'm going to rewrite this now. 3 times 2 is 6, square root 5 times x times 5 times 3 times x times x times x. Now, even though these two terms were simplified before we multiplied them, by multiplying them, we can see we end up with some more perfect pairs. So 5 and 5, x and x, and then another pair of x's. So just like with the numbers, we're going to do the same thing with the variables. I'm going to first look for those perfect square pairs. The first one we had was 5. So I'm going to move those to the outside of the radical. So 6 times 5, and then inside the radical we'll see what's left over. So we got rid of the 5's. Next factor pair we have is 2 of the x's. So we move x outside. That represents this pair. And then we have one more pair of x's. So when we take the square root of x times x, we get x. Now we look at what's left. And all that's left is the number 3. So from here, we are going to multiply all those terms on the outside together. So 6 times 5 is 30. So this would be 30x squared times the square root of 3. And that's our final answer, because we've found the prime factorization of everything we possibly can, and that has allowed us to simplify what is left. All right, let's keep going. In our next examples, we're going to multiply some more radicals. So just like we did before, first I'm going to combine the outside terms. So in this case, it'll be 1/2 times 4. And then within the square root, we're going to look for those prime factors. So the first one was 21, the first number. So that's 7 times 3. And then 7, which is just 7. Now we're going to write it all out in expanded form. So 7 times 3 times x times x times x. And then, let's redo this page. All right, so in our next examples, we're going to multiply some more radicals. First, we're going to start by finding our factor pairs. So for 21, we're going to break that into prime factors. That would be 7 times 3. And then 7 is already a prime factor, so that's just going to stay 7. Now we're going to combine the terms on the outside of the radical. So that would be 1/2 times 4. And then we're going to write everything else out inside the radical in expanded form so we can see all of our factors. So 7 times 3 times x times x times x times 7 times x times x. So that represents now 21x cubed times 7x squared. Here is where we look for those factor pairs. Now I see I have 2 7s now that I've multiplied those radicands. And then I have a pair of x's and another pair of x's. So let's simplify this. 1/2 times 4 is 2. And then we have 2 7s, so we're going to pull that out. 2 x's, so that comes outside the radical. And then another pair of x's. Now we look at what's left over. 3 and x, so inside the radical is 3x. Now our final step is to combine everything that's all outside the radical by multiplication. So 2 times 7 is 14. X times x is x squared. And inside the radical is 3x. So we end up with 14x squared times the square root of 3x. All right, let's do another one. Now I encourage you to pause this and try this one on your own to make sure it makes sense. This one, however, I already notice, we got some big old exponents. So I could write all of those x's out, 9 of them plus 5 more. Or like we did before in our first example, we can just look for those perfect squares by looking for the exponent of 2. So here's what I mean by that. First, we only have one term outside the radical, so we're just going to keep the 2 by itself. And then inside the radical, we have 12, which is 4 times 3, and 4 is 2 times 2. So this would be 2 times 2 times 3 times, and then we have x to the 9th. So we're going to do x squared. That's x squared plus, or times x squared, so that's 4 times x squared is 6 times x squared is 8 times 1 more x is 9. So that's our expanded form of our first radicand, but notice how I've run out of space. If that happens, try and stay as neat as possible because it is going to mess you up if we miss any factors. So what I'm going to do is just write within this radical, I am going to write it underneath just to make sure I don't forget any factors. So now for 18, we have 9 times 2, and 9 is 3 times 3. So we're going to write 2 times 3 times 3. And then here we have x to the 5th power. So that's going to be x squared times x squared times x. Now we can look for those factor pairs. I see I have a pair of 2's, a pair of 3's, and then a pair of x's, another pair of x's, another pair of x's, a 4th pair of x's, a 5th pair of x's, and a 6th pair of x's. Whew. So now let's pull those out. But first, I notice I might have missed something. Can you spot it? Even though they didn't have an exponent of 2, when we wrote out our expanded form, we see that the first radicand had 1x left over. The second radicand had 1x left over. But when we multiply those radicands, those can now be viewed as a perfect square pair. So now let's pull out those radicands from the radical, or those perfect squares from the radical, I should say. So we already have 1, 2 out there. And then we have another pair of 2's, a pair of 3's, and then 1, 2, 3, 4, 5, 6, 7 pairs of x's. So that would be x to the 7th power, representing how many perfect pairs we had. Now what's left over? 2 and 3. So our final answer, 2 times 2 is 4, times 3 is 12, x to the 7th times the square root of 6. That is our final answer. Now, the last thing we're going to learn right now is how to divide our radicals. When we're dividing radicals, we're kind of using similar steps, but there's an important rule to know. When we're dividing radicals, we can kind of distribute that radical to each piece individually. So let's look at our first example. We have the square root of 100 over the square root of 25. So that would become the square root of 100 over the square root of 25. And then if we're comfortable with our perfect squares, we recognize that this is the square root of 10 times 10, and this is the square root of 5 times 5. So since those are both perfect squares, we can take the square root of each, and we end up with 10 over 5. Notice there was nothing else left inside of the radicals when we took our perfect square pairs. So that simplifies to 2. All right, now for our next example, we have 63 over 98. The first thing we're going to do is simplify our fraction. So let's do that. when we simplify our fraction, meaning the terms inside, those can both be divided by 7. Simplifying fractions, just like we would if there was no radical, we end up with the square root of 9 over 14. Now, once we do that, we can see, oh, 9 is a perfect square pair. All right, in our next example, we have the square root of 63 over 98. Now, unfortunately, unlike the last time, these are not perfect squares, so we can't just, nice and easy find the square roots and simplify the fraction. But what we are going to do is simplify our fraction first before we start looking for those factor pairs and our perfect squares. So 63 and 98, those can both be simplified by 7. So that becomes the square root of 63 divided by 7 is 9. 98 divided by 7 is 14. So if we use our quotient property, we can rewrite this as the square root of 9 over the square root of 14. Now, as we become more familiar with our perfect squares, we know the square root of 9 is 3 times 3. So we could rewrite this as 3 square root 14. However, we cannot have a radical in the denominator of a simplified radical expression. So what we do here is we are going to multiply by the square root of 14 for both of these. Now, by doing that, we end up with 3 square root 14 over, and then let's look at this. If we have the square root of 14 times the square root of 14, that's a perfect pair. So that just simplifies to 14. So now we no longer have a radical in the denominator, and this can be our final answer. So if you end up with a radical in the denominator, multiply both the numerator and denominator by that radical. All right, that will simplify it, that will cancel out the radical and move it to the top. Now, this is your turn to practice. Use this video as a reference as much as you need during your homework, but your homework is listed here. You are going to do some questions in the textbook, and then we are going to go over these the next time I see you in class.